Hi guys, we're Group 60. My name is Raven.UPSB.
Hazel Hoots.
I'm Mikey Aguilar.
Kelsey Holian.
And today we'll be introducing you guys the concepts of momentum and the conservation of energy today.
A 10-gram Nerf bullet is fired into a 25-gram ball hanging from a meter-long string. The bullet hits the ball, and the ball then swings out to an angle of 30 degrees. What was the speed of the bullet?
Energy. Energy is everywhere. Any object that's in motion has energy, but in this case, we talk about kinetic energy, which is the energy of motion. So any object that is moving has kinetic energy. In other words, when an object has more mass, or when an object has more speed, it has more kinetic energy. In this video, we also talk about the law of conservation of energy, which states that energy can be transformed from one kind to another, or can be transferred from one system to another system. Alright, here is a diagram of the demonstration of the Nerf bullet onto the ball, where the Nerf bullet is 10 grams, and the ball is 250 grams, and the length of the string is 1 meter, and after the bullet hits the ball, it produces a 30-degree angle.
The first step of the problem is to determine the momentum of the Nerf bullet. What we're going to do is multiply the mass of the ball times its initial velocity, which is 0, plus the initial velocity of the Nerf bullet times its mass. Combined, that will be the combined masses times the final velocity. We need to isolate the initial velocity, so what we're going to do is take this equation and divide it by the mass of the Nerf bullet.
Okay, so for part 2 of the problem, since energy is conserved, we have the sum of the kinetic and potential energy final equals the sum of the kinetic energy plus the potential energy initial. So, the definition of kinetic energy is 1/2 times the combined masses times the final velocity squared. And for the definition of potential energy, we have the total mass times its gravity and its final height, which is, and we could also say this for the initial part of the equation. Since the ball is hit by a bullet, eventually it's gonna move back and it's gonna get a velocity equals to 0. So that's why this part goes to 0. And we define that the initial height is 0. So we can also eliminate that. Given this, in order to find the initial velocity, we could multiply by 2 and take the square root. Therefore, getting the square root of 2 times gravity times the final height, which equals our initial velocity.
Okay, so everyone, just as Raven explained with this conservation of energy formula here, he derived with this from a root 2 times gravity times the y final, which is going to be the length of the string initially in the diagram that Mikey explained over here, which is going to be 1 meter. Now, after the bullet hits the ball, it's going to come with a 30-degree angle, just as Mikey explained earlier, and we're going to get a length of L cosine theta, which is the max height that it reaches between the initial point of the connection of the string to the connection of the ball. Now, once we go back over here, we're going to use this formula right here to solve for that problem, to get the initial velocity from the formula that Raven explained earlier. So we're going to take the L minus the L cosine theta, which is once we plug all the numbers in, 1 minus 1 cosine 30 degrees from the angle equals 0.134 meters, equals the length of the string, L final. And then once we plug this into the formula here, root 2 times 9.8 times 0.134, we're going to get an initial velocity of 1.62 meters per second.
Okay. Now that we have found the initial velocity of the system, this initial velocity of the system is also the final velocity of the exact moment when the bullet reaches the ball. So returning back to the equation that Kelsey derived, we now know the final velocity and we also know the masses. So by plugging in all the masses together times our velocity of 1.62, we get the result of 42.12 meters per second.